Hi, this is the pre-lab lecture for the E1 lab for Chem 344. So what we're going to start with is this compound, this 1-methyl cyclohexanol. Sorry, it's 3. And we're going to submit it to acid treatment. And this is going to produce a variety of alkene products. And the way this happens is, if you remember from your organic chemistry classes, the first thing that will happen is the acid will react with the alcohol, the greatest nucleophile in this system. And this makes a really good leaving group as water. And this can undergo an elimination to form any one of these products. So it gets really interesting to examine the theory of which ones are most prevalent, but some data that I was given not in your lab manual show this trend. That is the enthalpy of formation, so it's kind of like a thermodynamic measurement of what's the most likely to form in this reaction. It's a really common way of establishing, theoretically, beyond what we observe experimentally, like why things are the way they are when it comes to mixtures of products. And then what? So what this is saying is this substituted product is more stable than this one, which makes sense, right? Because this is a substitution at a tertiary position rather than a secondary. And this is the least stable. Even though it has a substitution at this tertiary position, this has no substitution on its end. But we still will see this form. In fact, we can make this the more common product by dragging out the reaction longer. The reason this is because it can go through a hydride shift here to form a really stable tertiary carbocation, right? Because this hydrogen moved here. So that's all that. If you have more questions or my drawings suck, please come to my office hours. And the next key part that I'm going to talk about is calculating the percent yield. We calculate percent yield differently than percent recovery. So what we'll do is we'll put the actual yield over the theoretical yield. And since we're going for a percentage, we always multiply by 100%. Let's try not to stand. Okay, and so the theoretical yield is not the same as the grams of cyclohexanol. So what we need to do is we actually need to convert the grams of cyclohexanol into the grams of the hexene mixture. Et al just means others, so the mixture of isomers that we saw. But since anyway, so let's get back. Actual over theoretical. how do we do this calculation? We use dimensional analysis. So you'll start with a mass amount of grams of your cyclohexanol mixture. I'm going to give you this number. One of your classmates is going to record it in class. And then you'll multiply it by the molar mass. So we want to go from grams of cyclohexanol, so we need to convert to moles. So you're going to use the molecular weight, which of this one, so that's a number that you'll look up. And since we're converting now, we're going to convert to grams of the hexane, of the alkene product. And you might be wondering, well, this isn't the only product. We have 3 products. But don't worry, all 3 of these have the exact same molecular weight because they're all isomers of each other, right? And this will give you the grams of your alkene product. Okay, so once you have the grams of the alkene product, that'll give you your theoretical yield. Oh, and just to be clear, yeah, because we're working in mils. Okay, yeah, so hold on. Let's backtrack here really quickly. So we've got to get to grams of this, and we're starting in mils, right? So let's say someone measured out exactly 1.5 mils. Well, then we'll just convert using the density of that alcohol. So I think I looked it up, it's like 0.93 or something. So that would be times 0.93 grams per mil, and that'll give you the gram amount. Okay, and so, yeah, this will end you with the theoretical yield, but there was probably some lost along the way, so you're going to get the actual yield from a student. I'll give you that data. This is a measured amount. And again, this value is going to be in milliliters. So you're going to have to convert based on the density. Yep, okay. If you have a hard time with dimensional analysis, like it's hard for you to remember which goes to what, because I know you're probably thinking, why is this moles over grams? Isn't molar mass typically grams over moles? Well, that's the thing, is we're trying to convert to moles, so I flipped it. So the bigger number is going to be down here. The reason I did that is because when you're doing dimensional analysis, you always want to have your new units on the top. A way I like to remember this is when you're looking at like a fraction. This is dorky, but this helps. The sun always rises to start a new day, just like you will always have the new units on the top in the numerator. Okay. Okay. So the other calculation that you're going to need to have in your results is they're going to be the relative areas of the peaks. So I'm going to give you GC data, and let's say it kind of looks like this. Now we need to calculate the relative areas of all of these peaks. So based on the theory I gave you, you would assume that peak number 1 is this one, because this one has the lowest boiling point at 102.5 degrees C. So since it has the lowest boiling point of all of these values, it's going to come out first on the GC. Right, so let's say that it comes with a table on the side that shows you that peak number 1 has a total area of, what did I put? 8, and then the next one 24, and then the next one 72. We want to calculate the relative areas, so a ratio of each peak. So the way you're going to do that is first you're going to identify the smallest peak, the lowest area. Obviously that's number 1 at 8. So we'll set this factor equal to 1. The way we do that is we just do, it's 8 over 8. Include units, and that'll come on the GC data, but I'm just trying to explain to you the theory right now. So this one has a relative area of 1. Now let's move on to the second peak and compare the size of this area to the first area. This one's at 24, so 24, again over the smallest one, 8. So that puts us at 3. So this one has a relative area of 3 to 1 to the first peak. Now we're going to calculate the biggest one, which is at 72. Nine. So it's a 9 to 1 ratio of our most stable product to our least stable product, or to our minor product, our major product to our minor product. Yeah, so you'll do this with data I give you. And use units, even though I didn't. I'm sorry. Ratios are a unitless value. Okay. Again, office hours for questions. So in the conclusion, I want you to discuss the relative areas. I want you to talk about why you sell more of one product over another. And I want you to explain the yield. It's not as important, but it is important to talk about the theoretical reasons why there might have been loss. And the way, I know it's going to be hard because you didn't actually do the experiment to visualize why this happened, but pretty much every time in the lab report there's like a warning, something like don't boil it too high, use wool as a fractionating column. All of the times there's like a little warning. That's a place where there can be a pitfall in the lab where you can lose yield. So you can just talk about those things and based on what you think are the most important factors. And as usual, you're never going to be marked off for bad data. That's just like not a great result. Okay. Yes. So on the like final questions, there are two kind of challenging ones. The first one is talking about the wool that you're going to put in the flask. So it's supposed to act as a fractionating column. This is the wool right here. And the way it works is it allows liquid to come up and then recondense back down, right? Just like a regular fractionating column. And the reason we want to do this for this lab is because we're separating a high boiling compound, the alcohol, and from a low boiling compound, the alkenes. And this really, having the fractionating column really helps with that separation. Another good question is they ask us why we use molecular sieves. So molecular sieves absorb water. They're just like little pillows, and they just soak up water. In the E1 reaction, water is our leaving group, right? So through using Le Chatelier's principle, it's going to pick up water from the reaction. And that's why we use it. It's a little confusing because with using 85% phosphoric acid, you actually do have about 15% of water in the mixture already. So it's probably inundated with water, but through experimental analysis, we found that using these sieves is actually still pretty effective. And that should wrap up the pre-lab lecture. If you have any questions, send me an email.